So let's take a look at our first example for the scalar product. And first things first, we always need to read. So here it asks you to find the parallel force component in AB due to the 300 Newton force, which is acting parallel to the XY plane. So let's take a look at this picture here. So this force here, 300 Newton, is only parallel to the y-axis, and it's acting in the XY plane, if you will. So there's no Z component, there's no X component either, but the force is acting parallel to the XY plane. And then you have this structure here from A to B, and there are some legs attached, but they are not even marked. Let's forget about them. In fact, if you read this note here, it tells you to ignore the legs of the tripod. Technically, that can lead to complications in terms of how the load is distributed throughout the structure, but that is not our concern here for beginning engineering mechanics. That's not our worry. In the real world, it would look a little bit different, but let us just consider pipe AB here, which moves from 0 z-axis to a height of 3 meters. So that is obviously not parallel to this force. No matter how you look at this problem, this force is acting in the XY plane, or better I should say parallel to the XY plane, and AB is slanted or sloped upwards, and it's not acting in any plane that we see here. So that means that we have to understand a very important concept, which sometimes, based on my experience in the classroom, is not easily understood by students, but maybe I can zoom in a little bit for you and make you think about this. So I want to identify pipe AB for you here, which once again is not parallel to the force. So what that means is that we actually, if we extend that pipe, which I'm going to do here now for you, there is a triangle that the pipe forms with the force. And if I want to complete that triangle, let me draw the perpendicular component to it. So I also have this part here. And so now I have 3 parts, which is technically vector decomposition, or is nothing else than vector decomposition. And what we have here is first the 300 Newton, which is in blue. And then let me call that F1. So now I can determine that there must be an F1 that is parallel, right? So, and technically that should be F1, and then the sign for parallel is this, but I didn't want you to be confused with the 1 and the parallel sign. But you also understand that there's F1 perpendicular. So that is a concept that needs to be really visualized by engineering students. They need to understand that a force that is not acting parallel to a member always produces 2 components. It produces a force component that is parallel and one that is perpendicular. Let's not really worry about the perpendicular one right now. I know that often students get confused about this initially, but we will talk about this later, and actually we'll talk more about this in follow-up classes. Because one confusion that always comes is like, in which direction is this really acting? Is this acting away, or like, is it acting towards me? Is it acting away from me? Is it acting in a random direction? Is it defined? Those are things we are not worrying about. What we are worrying about today is the parallel force component. And you probably already understand that there's an angle between these two. We will not worry about this angle today, but you know that there's the angle theta here. And so therefore you understand that you can actually project effectively this force onto this extension of the structural member. And so we can really apply the scalar product now to find the parallel force component along AB. And I believe it's a good time for us to do that now. But once again, I want you to understand that we have always 2 components that are the result of a force acting not perfectly parallel or not perfectly perpendicular to a member. So of course, if your force was acting perfectly parallel, then you wouldn't have a perpendicular component. If your force would be acting perfectly perpendicular, then you don't have a parallel component. But any other force, like this one here, would always produce a parallel and a perpendicular component. So let's calculate that. Because remember, I write it once again, A dot B is equal to A B cosine theta. But the question is, how does this apply in this case? So in this case, we have two vectors. We have a force and a position vector. So my force F1 is already given to me, but I'm going to write it out anyway. So F1 is nothing else than 0 I hat plus 300 J hat plus 0 K hat. And this is given in newtons in this case. And now for the position vector, let's call that AB. That is a vector AB. Now, what is that? Of course, you know this from your basic math class. In the x direction, I'm going positive 2. In the y direction, to get from A to B, I'm going positive 6. And then in the z direction, I'm going positive 3. So let's write that down. So everything is positive in this case. So plus 2 I hat plus 6 J hat plus 3 K hat. And that in this case here is given in meters. And I want you to understand now that it's a difference if I go from A to B or from B to A. And the question here asks you to find the parallel component in AB, not in BA. So be careful with that. So we're moving in this direction. But remember what I tried to allude to earlier, that the force, the parallel force here, is projected by F onto the extension onto pipe AB, right? So if you now were to apply this formula blindly, let's say the full magnitude of A and the full magnitude of B, and then you take the cosine between them, then you would pretend that the 300 has a higher impact on a longer pipe. So the longer this pipe AB would be, the more parallel force you would have due to the 300. And that is not possible physically, right? So you have to understand that the parallel force component in this pipe is only dependent on this magnitude and has nothing to do with the magnitude of AB. So what that means is that I need to find the unit vector of AB. And let's write that down. So AB hat is nothing else than 2 I hat plus 6 J hat plus 3 K hat. And then the whole thing divided by its magnitude. And the magnitude is 2 squared plus 6 squared plus 3 squared and square rooted. And if you run the numbers, you will find that the square rooted term is actually 49, which then is 7. So we have 2 over 7 I hat plus 6 over 7 J hat plus 3 over 7 K hat. And keep in mind that here we have meters, but here we have meters as well. And so therefore our unit vector now is actually equal to unitless. And that is something that must be the case, otherwise it wouldn't work, right? So if you were to usually multiply this by this, so a force in newtons by a distance, then you would end up with what's later known as a moment, so Newton meters, and that cannot be the case because we're really looking for a parallel force component. So you need to somehow get rid of the meter here, which that is another reason why you have to turn the second vector into a unit vector. But now we can run the math, which is really not that difficult. So we now have F1 dot AB hat, and that is effectively equal to, let's write it out, 0I plus 300J plus 0K. and that is dotted onto, well, let's use a unit, dot onto 2 over 7 I hat plus 6 over 7 j hat plus 3 over 7 k hat. And that is unitless once again. And so now if you run your general concept, remember that it's just component plus component. So 0, well, let's write that out as well. 0 times 2 over 7 plus 300 times 6 over 7 plus 0 times 3 over 7. And of course, all the other numbers fade away because they are 0. But ultimately, what you will find is that you end up with 257.1 Newton. And this is actually a result. So let's mark that as a result. And let's analyze that result and ask ourselves if this makes sense. And in my opinion, it does make sense. Why? Because it is less than 300, and that's very important. That's a check you can run in your exams and in your engineering real world. You need to make sure that the hypotenuse is longer than your parallel component or your perpendicular component. That cannot be any other way. That's why it's called the hypotenuse, right? So here, my parallel component is really less than the hypotenuse. In fact, I probably should write down that this here is really F1 parallel. And that is also a magnitude. That's the other thing to understand here. So like I said at the beginning of the lecture, sometimes students magically use the dot product and end up with like something ijk, and that's not possible. So we only found the length of this vector here. And the length must always be just a number or a scalar, right? So the length can only be a scalar. So this is a magnitude. Please don't forget this. Now you may ask yourself, but we always have to give magnitude and components. So how do I get my components? How do I know exactly ijk of this force? And the answer is right in front of you here actually, because you already know the direction of this force. The direction of this angle or of this parallel component is given along this line. And what is the line? The line is given by this unit vector, because the unit vector AB hat describes the direction of this pipe and therefore the extension, which is the parallel component. So to find the F1 parallel as a vector, what you have to do is you have to take your 257.1 Newton and multiply that by your unit vector. So in numbers, that would be 2 over 7 I hat plus 6 over 7 j hat plus 3 over 7 k hat. And if you run the math here, what you will find is that you end up with 73.5 I hat plus 220 j hat plus 110 k hat. And this once again is in Newton. So now I end up with another result that is part of my answer. So I better provide an answer arrow. And in this case, I am technically done, because let's take a look at the problem statement. The problem statement asks us to only find the parallel force component. And technically, this could have been interpreted as being done here, but when you find vectors, you always give the magnitude and the component form. So let's, however, for educational purposes, talk about further implementation of this and the fact that you could, as I mentioned to you before, now calculate the perpendicular component, right? So you could calculate F F1 perpendicular, simply the magnitude of it by using the Pythagorean theorem, which would be F1 squared minus F1 parallel squared, and then the whole thing square rooted. So if you use numbers for that, what would you end up with? You would have 300 squared minus 257.1 squared and then square rooted, which, if you calculate that out, ends up to be 155 Newton. Or you can actually find the vector in this case, F1 perpendicular, by subtracting the components as well. So remember, you have 300 j hat, and then you subtract the 73.5 I hat plus 220 j hat plus 110 k hat, and then you will find that you actually end up with minus 73.5 I hat plus 80 j hat and minus, be careful, right, minus 110 k hat. And that again is also in Newton. And now if you were to take this result and you take fx squared plus fy squared plus fz squared and you take the square root of that, you will find that you end up with 154.6 or something like that, which is really almost 155. So that gets a check. And therefore, we are now at the end of this problem, and we solved actually more than we were asked for, because we now have the parallel component and its perpendicular component. And I believe this is an important concept for engineers to understand. The math, in my opinion, is often not the problem to get across to students, like many things actually in mechanics, because the math is very simple if you think about it. The problem is to understand the physical implementation that we tried to derive here at the beginning of this problem. So I encourage you to really study that deeply, because you will have to set these problems up yourself. So you have to find the proper expression for F1 and for AB and AB hat. Of course, it's not always AB, like we will give you different problems, but please understand that you have to read the sketch and then turn it into a calculation. And applying the calculation is usually not the problem. The problem lies here. However, I think I stressed that enough now, but I want to mention one last thing because it's so important and I see it being confusing so often in the classroom, and that is to understand that any force that is not parallel to a member always produces a parallel and a perpendicular component. And that is something some students need to be harder convinced about than others, but please try to somehow grasp that concept. It will come later on in many, many different forms, not in the form of dot products anymore, but you will see forces that have to be broken down into parallel and perpendicular components. So this is a concept you need to understand deeply. Please make sure that you get there. But this concludes this problem, and now we're ready to move on to our last example. So let's take a look at our last example in this lecture here. I will not really solve this for you, I leave this up to you, but I want to at least derive the problem for you. So here you have to determine the parallel force component in member BC. So take a look, there's B and C, due to the force FC, which pulls on the pipe structure ABC. So be careful here. This, if you're already advanced in engineering, this can look like you need to do much more than what we're asking here of you. But really what we're after here is the force in that pipe BC. So let me mark that for you in red. So here we have a vector which is BC, and clearly what we want is BC head, right? Remember that we want to project FC onto BC. So really what we're looking for here is FBC parallel due to FC in pipe BC. So what we need is FBC parallel, which is nothing else than FC dotted onto BC, but now be careful, head, right? So BC head is what we need in this case. So let's derive that vector first, because FC is already given. I don't need to do anything about that. So FC is given to you right here. I don't have to write anything. But we need to derive BC. So first BC. So how do I do that? I need to go from B to C. How do I get there? I actually, don't be fooled, I do not have to go upwards, right? So the 4 here refers to how far you have to go from A to B or from A to C in the Z direction. So I don't have to worry about that. However, I have to go into the positive X direction by +1 I hat. And then in the positive Y direction with 5 +5 J hat. And then +0 K hat. And this is in meters. And so to get my BC head, I need actually BC magnitude, which is equal to 1 squared plus 5 squared plus 0 squared, and that's square rooted. And you can calculate that to be the square root of 26. And then last but not least, your BC head is equal to 1 over square root 26 I hat plus 5 over square root 26 J hat. And plus 0, I don't even bother writing that down. But that again is unitless. And now you can use that in your equation right up here. And there's no need for me to bore you with that. If you need the mathematical procedure, you can find that in the previous example. But I encourage you to really think about that. The last thing I'm willing to do for you here is to visualize it for you. So we have a parallel component here, and we have a perpendicular component right here. So this would be FC perpendicular and then FC parallel. Be careful, depending on where the arrowhead points, right? You also have a force that goes in that direction or in the opposite direction. So let me add actually the directions here for you, which here is very similar to what before, but it's not always that case. Sometimes it is actually not pulling, right? So here it's explained to you because it's the first educational problem, but sometimes that's different. Be careful about that. Understand that we have the right angle here, and also understand that here you have a negative number. It's pulling in the negative X direction. So that means that you have to watch out for your combination of your dot product here when you do FC times BC. But again, the goal here is not to run the numbers for you now. I think the problem has been deciphered. You can definitely now go ahead and solve this and use it as a practice problem. I wish you good luck with that. I think it's time to move on to our last page in the lecture and check our boxes.